So let's start with a couple of announcements. So I'm traveling this week. That's why today's lecture is recorded. And because of my travel, class on Wednesday, September 12th, will be cancelled. And also office hour today is cancelled. But please, if you have any questions, send me an email, and I'm sure we can work something out. So homework 1 is released today and will be due on September 17th. So the topics that are covered in this first homework assignment include the lectures that we've had so far. So it's going to be about Big O, it's going to be about global alignment, and it will also include topics in today's lecture. So what I want to talk about today is I just want to recap global alignment again, just to make sure that you guys really got it. And I also want to look at 3 different variants of alignment: fit-in alignment, local alignment, and gapped alignment. So the material of today's lecture is in the book. It's in chapters 6.7 to 6.9. And I also wrote a couple of lecture notes on today's lecture. So please take a look at that as well. So before we start with alignment, let's talk about Big O again. So this is something that will also be in the homework assignment. So last time we saw that n factorial is Big O n to the n. And we derived this using Stirling's approximation. So Stirling's approximation states that n factorial asymptotically equals this right hand side over here. And if you rewrite it a little bit, you arrive at this part over here. And if you look at this factor, square root of n divided by e to the n, so square root of n is dominated by e to the n. So that's why this ratio is at most 1. So square root of 2 pi is a constant, so that drops out at a big O. This ratio is at most 1. So that's how we got the n to the n. So that's how we got n factorial equals big O n to the n. Now n to the n is equal to 2 to the n log n. So this log here, so actually logs in the exponent, the base matters. So constants in the exponent matter in big O. So if the base is 2, you can easily see that you can swap these 2 factors over here. So you can also write this as 2 to the log n times n, and 2 to the log n equals n. Hence, why you have n to the n equals 2 to the n log n, where the base of the logarithm is 2. Okay, good. So that's why n factorial equals n to the n, which is 2 to the n log n. So now the immediate question arises is whether n to the n is big O of n factorial, whether the reverse holds. So in other words, are there constants c and n0 greater than 0, such that n to the n is at most c times n factorial for all n at least n0. So let's think about this a little bit. So one way to think about this is to look at the ratio of the 2 functions. So if you divide n to the n by n factorial, and if you look at the limit of this ratio as n goes to infinity, what happens? So let's try and work that out. So we're going to look at a ratio of n to the n divided by n factorial. So n factorial equals n times n minus 1 times n minus 2 all the way down to 1. So this first factor here, this n is going to cancel out immediately. So you get n to the n minus 1 divided by n minus 1 factorial. Now let's look at these individual factors in isolation. So we can rewrite this as a product of n over n minus 1, where I runs from 1 all the way up to n minus 1. So if I equals 1, you get this factor over here, n minus 1, in the denominator. And if I equals n minus 1, you get 1. So if you look at these, if you look at every ratio in this big product, you can see that the numerator is greater than the denominator, and the denominator is non-negative. So this means that every ratio in the product, as n goes to infinity, every ratio will also go to infinity. So this means that the whole limit of n to the n divided by n factorial goes to infinity, which means that the function in the numerator is asymptotically larger than the function in the denominator. So in other words, we won't be able to find a constant c that's going to be able to accommodate this function over here. So no, so n to the n is not big O of n factorial. Very important, keep this in mind. Good, let's continue with alignment. So global alignment. So we're given two strings, v and w. So string v has length m and w has length n. And we're also given a scoring function delta. And the task is to find an alignment with maximum score. So what is an alignment? An alignment is a source to sink path in the edit graph. Alternatively, we can also view an alignment as a matrix. So this is a 2 times k matrix. So the two rows of the matrix correspond to the two input strings. So the first row is string v. So if you remove all the gaps, you get string v from the first row. And if you remove all the gaps in the second row of a, you get string w. So that's this condition over here, condition number 4. So in addition, what we also have is that there is no column in A containing 2 gap characters. So every letter of the input sequence, of either input sequence, needs to be matched with another letter from the other input sequence or with a gap. So this means that the smallest alignment has length maximum of m and n, the length of the shortest of the longer sequence among your input, and the maximum alignment length is m plus n. And in this case, every letter of any input sequence will be matched with a gap. So those are alignments. So can we characterize the alignment with maximum score? And the answer is yes. You can do this using a recurrence. So the recurrence Sij indicates the maximum alignment score when aligning the first I letters of V with the first J letters of W. So the score that we are interested in is S of M and N. So that will be the entirety of string V and the entirety of string W. So if I equals 0 and J equals 0, that's our base case. So we're aligning two empty strings. So when you align two empty strings, the score of an alignment is simply the sum of the scores of the columns. So if you have no columns, you're essentially summing over an empty domain. So that's going to be equal to the identity element of addition, which is 0. So that's why the base case equals 0. So the second case is a deletion. So you align a character of your first input string V with a gap. So, and the cost that you pay is indicated here by this delta VI gap. So this is typically going to be a negative cost corresponding to a penalty. So similarly, the third case corresponds to an insertion. So we insert a gap in the first string with score delta minus delta gap Wj. And the fourth case corresponds to a match or a mismatch. So if we have a match, so if Vi equals Wj, we'll typically see a large score in delta. And if there's a mismatch, this score is going to be much smaller, can even be negative. So that's global alignment. Now, last week I started introducing finite alignment, so I just want to give you the motivation again. So the motivation comes from short read sequencing. So if you think about a human genome, we have 3 billion nucleotides, 3 billion letters. However, when we sequence a sample of human cells using next generation sequencing, we get a large collection of short reads, and each short read has length 100. So our input sequences that we observe, the short reads, are orders of magnitudes shorter than the human reference genome. And in addition, when you look at these short reads, they won't be the same as they won't be substrains of the human genome because of sequencing errors, and also because of mutations and polymorphisms in the cells that you look at. So the way to think about this is that not every human is identical. So there will be differences in the genome, and these differences will occur in the short reads. So essentially, we do want to solve an alignment problem. However, if you use global alignment, you will try to align the entirety of your short read with the entirety of the human genome. So that's going to introduce all kinds of problems. So you need a lot of gaps to make them fit, and you will pay for those gaps in your scoring function. So global alignment is not a good idea. So how can we account for this discrepancy between length of the reference and the length of a short read? So here I'm just illustrating what's going on. So W is the human reference genome, 3 billion letters, and V is just a short read, 100 letters. So the immediate problem that we can get from this is we basically want to align the short read to a substrain of the reference genome. So let's state this mathematically. So we're given two strings, V and W, and a scoring function delta, and the task is to find an alignment of V and a substring of W with maximum global alignment score. And this maximum global alignment score is among all global alignments of V and all substrings of W. That's great. So we actually have our string V, and we want to look at all possible substrings of W and solve a global alignment problem. So the way I stated this already gives us an algorithm. This immediately gives us an algorithm. So what we could do is we could simply construct all possible substrings of W. So a substring of W, a non-empty substring of W, is defined by two indices, I and J. So I is the starting position, and J is the ending position. So we require that I is at least J. So how many such substrings are there of W? So if you look at I smaller than J, strictly smaller than J, you basically get the nested for loop example, right? So you have two for loops. I goes from 1 to n, and J goes from I plus 1 to n. So the number of times this for loop runs is n choose 2. That's what we saw last time. And so what we have is we have n choose 2 plus n. And so this plus n, this term n, occurs when I equals j. So that's the number of global alignment problems that we want to solve if we brute force this. So we're going to solve a global alignment problem for every substring of W, and there are n plus n choose 2 substrings of W. So if you look at the running time of global alignment, it's the product of the input lengths. So in this case, so we cannot simply say that the running time is going to be m times n plus n choose 2. So in other words, mn squared. Because if we would do that, we would essentially assume that each of these substrings have length 1. So we actually need to take the lengths into account if we want to compute the running time. So let's do this more carefully. So this is in today's lecture notes. So let me just pull those up. So we want to compute the running time of the naive fitting alignment algorithm. And in the naive approach, we will generate all possible substrings of W and solve the corresponding global alignment problem. And the question is, what is the total running time when we take the sum of the running times of each global alignment instance? So what I told you is that an alignment, a substring of W is defined by two indices, I and J. And so essentially what we want to do is we want to compute this term over here. So we want to look at the running time. So the length of our input sequence, of our second input sequence, W prime, is J minus I. So if J equals I, we basically have a substring of length 1. And the running time is going to be M times the length. And we look at all possible substrings. So that's this big double sum that we have over here. So when you look at this more carefully, you can see there is a big constant over here, this M. So we can distribute it out. So we have big O of M times the double sum here. So this is the thing that we need to compute. Now let's look at this a little bit more carefully. So J minus I, that's the length of the alignment. That's the length of the alignment of the substring W prime. So how many substrings of length 1 are there? L equals 1. So there will be I equals J, and I runs from 1 to n. So there are n substrings of length L equals 1. Now you can use the same reasoning to think about substrings of length 2. So they would correspond to ij, where j equals I plus 1. And there are n minus I such pairs. So that means there are n minus 1 substrings of length 2. And this continues onward. So if you look at substrings of length 3, then we're looking at pairs I, I plus 2. And there are n minus 2 such substrings. So in other words, we can rewrite this left-hand side as a simple sum where the length runs from 1 to n, and we're essentially counting the number of alignments with that length. So that will be the length times the number of alignments with that length. So if the length equals 1, L would correspond to 1, and there are n substrings of length 1. So that's what this right-hand side tells us. Now, if we rewrite the right-hand side, what we get is, so let's just multiply things out. So we get ln minus L squared plus L. So we can simplify this. So we essentially have 3 big sums here. So the first sum is L times n. So n is a constant, so we can put it in front. We distribute it out. And then we have a sum of L squared minus L squared. So that's this part over here. And then we also have L. Good, so this is what we get. So we get 3 sums. Now, if you look at this sum over here, the sum of L equals 1 to n of L. So that's a very familiar sum. So that's actually that's basically what we had when we were trying to do 2 nested for loops. So this corresponds to n times n plus 1 divided by 2. And similarly, when we square this, we get also a known series, which corresponds to this over here. So if we use these 2 identities, we can rewrite this as n times n plus 1 divided by 2. So I'm just substituting this sum over here with this identity of the series. And I'm doing the same thing here. So I'm using the identity. So this is going to simplify to n cubed plus 3n squared plus 2n divided by 6. So if we plug this back into the running time, what we will get is a running time of m times n cubed. So that's the running time of our naive fitting alignment approach. So the key point here is you have to be a little bit more careful when you do the running time analysis. So don't simply compute the number of substrains and then assume that every substrain has length 1 and multiply that by big O of m. That's going to give you the wrong running time. It will give you mn squared. But if you do the analysis more carefully, you can actually see that the running time is mn cubed. So keep this in mind. Be a little bit more careful when you do your analysis. Good. So the naive approach gives us mn cubed algorithm. So if m equals, so m is actually going to be much larger than n. So that's the running time that we will have. Can we do better? And the answer is actually yes, we can do much better. So what I did here is I just gave you the recurrence, the solution. So let me just motivate this a little bit. So what's going on is with global alignment, we want to, so this is the edit graph. With global alignment, we want to find the longest path from the source node, 0, 0, to the sink node, m, n. The longest path from 0, 0 to m, n. The longest source to sink path. So with fitting alignment, essentially what you have is your opening gaps are free. And your closing gaps at the end are also free. So this translates to basically starting anywhere on the first row and ending anywhere on the last row. That's really what we want to do. So we can capture this in the recurrence. So in the global alignment recurrence, previously the base case was I equals 0 and j equals 0. So we're going to change that base case. We're going to drop the j equals 0 because anywhere on the first row will be free. We'll have cost 0. And the value that we're actually interested in, so our ending point, that's going to be anywhere on the last row with maximum score. So that's really what a recurrence becomes. So what this is going to lead to is a path in the edit graph where the starting vertex is anywhere on the first row and the ending vertex is anywhere on the last row. So let's look at a simple example. So here I'm trying to align. So my longer string W is TACGGC and my shorter string is AGG. And let's use a match score of 1 and a mismatch and insertion deletion score of -1. So the optimal alignment using this scoring function corresponds to this over here. So the score will correspond to, so we have basically every diagonal edge in this case corresponds to a match, which you can see over here. So there will be a score of 3, and we have 3 gaps. And actually we have 3 total gaps, but the only gaps that count is the gap in here. So that would correspond to a score of 3 minus 1 equals 2. So I want to show you this website actually. So this is very cool. So it allows you to look at fitting alignment and actually see the table. So let's take a look at that. Should have it open here. So we're looking at, let me see if I copied the sequence correctly. So we have AGG, so that's our first string, and we have TACGGC. TACGGC. C, correct. And we're using a match score of 1 and a mismatch indel score of -1. So let's just change that. So gap penalty is going to be -1. So our match score is going to be 1. This is the mismatch score, so that's always going to be -1. And we're doing fitting alignment. right, so let's just take a look at this. So this is the same alignment that we had before. So we have A, gap, GG. So that's what we had here, A, gap, GG. And you can see that if you fill out this table, this is what you will get. And the maximum score on the last row is 2. And then you can do your backtrace from 2. So you will take this edge, that's the diagonal edge. So that leads to a match. So that's why you have a +1 here. You also have a +1 here. That's another match. And then you have a deletion. An insertion rather, and another match. So that's what we have over here. So if we try to solve the same input, so our score corresponds to 2. So that's what I told you. Now, if we try to solve the same instance using global alignment, what we get is a score of 0. So the alignment looks the same in this case, but you pay for the opening gap and the closing gap. So the gaps that you have in front and the gaps that you have at the end. So you start your alignment from here, from 0. So that's essentially what happens. Good. So that's fitting alignment. Now, let's talk about a different kind of alignment problems, which is in between global alignment and fitting alignment. So it's called local alignment. And the motivation comes from proteins. So proteins, so if you remember lecture 1, what we said was that DNA goes to RNA and RNA goes to protein. So proteins are basically the machines in our body that fulfill different functions. And if you look at the way proteins are structured, they consist of something that's called a domain. And these domains are pieces of sequence of amino acids that are actually conserved in different proteins and even across species. So you have domains that correspond to motility, you have domains that correspond to basically something that's called ATPases. So these are domains that are able to take ATP, which is like the fuel of a cell, and reduce ATP to basically get energy. So there's a lot of conserved functionality that is expressed using domains. Now, if you look at two different proteins and if you try to align them, maybe they will differ a lot, but there could be pieces that are similar that correspond to domains. So this gives rise to the local alignment problem. So in the local alignment problem, we're given two strings, V and W, and also a scoring function delta. And the task is different from global alignment. So rather than aligning V, the entirety of V with the entirety of W, we want to find a substring of V and also a substring of W whose alignment has maximum global alignment score among all possible substrings of V and W. So that's the problem we want to solve. So as I said, so this is in between global alignment and local alignment. So with global alignment, we wanted to find an alignment of the entirety of V and the entirety of W with maximum score. With fitting alignment, we were looking at substrings of W, of all substrings of W. And with local alignment, we're going to look at all substrings of V and all substrings of W. And they all use the same scoring functions. They all use the global alignment scoring function. So that's the key notion here. So the same scoring function, but you change your input. So with fitting alignment, you look at all possible substrings of the second input sequence, W. And with local alignment, you're going to look at all possible substrings of V and all possible substrings of W. So we can use the same kind of naive approach as we discussed for fitting alignment. So we can just generate all possible substrings of V and W, and for each pair of substrings, V prime, W prime, we can solve the global alignment problem. So the number of such substrings in big O notation is going to be m choose 2 times n choose 2. So there actually needs to be a big O here, which is going to be big O of m squared times n squared.
but they have different lengths. So this is not the running time. So if you want to look at the running time, it actually immediately follows from the naive fitting alignment algorithm. So essentially, what we want to compute is this term over here. So we want to look at all possible substrates of V, and we want to multiply. We want to look at the length, and we want to multiply that by the length of all possible substrates of W. Because the running time of a global alignment instance is the product of the two lengths of the input string. So from the analysis of fitting alignment, we know that the sum of the lengths of substrates of W equals this quantity over here, n cubed minus 3n squared plus 2n over 6. So similarly, we can use the same reasoning, and we will get the number. So the length of the substrates of V is going to be, instead of n, you will have m. So if you multiply these two terms, what you will get is something that's big O of m cubed times n cubed. So that's really slow. So if m equals n, we're talking about an n to the 6th algorithm. That will be the running time of the naive local alignment approach. So can we do better? So let's take a look at that. So with global alignment, we basically want to start at 0, 0 in the edit graph. That's the source vertex, and we want to edit m, n. Now with fitting alignment, we want to start anywhere on the first row and end anywhere on the last row. And the idea was that the first insertions are free before you match any character or mismatch any character. And the last deletions, the deletions at the end, they're also free. So you want to start anywhere on the first row and end anywhere on the last row. Now, with local alignment, we basically want to start and end anywhere on the matrix, because we can also look at substrings of the first input string of V. So we no longer have to start on the first row. We can start on the 5th row, for instance, and we can end anywhere. So that's going to correspond to a substring of V. So let's see if we can formalize this using a recurrence. So basically, so here I'm showing you the global alignment recurrence. In the global alignment recurrence, this is not striped out anymore, and you don't have this this last term over here. So with local alignment, we want to be able to start anywhere. So the base case is going to be basically, so you can always be 0 anywhere. That's really what it means. So if you're 0 in a cell, it means that you started at cell. And our target vertex, where we want to stop, is going to be anywhere in this matrix. So that's what this S star is. You want to be able to stop anywhere. So that's what a recurrence is. Start anywhere and end anywhere. So let's see what this looks like in practice. So we're gonna align AGG with TAC GGC. So that's the same sequence again. So let's take a look at that. So the match score is going to be 2, mismatch is going to be -2, and the indel will be -4. So we do local alignment. So when we have these two sequences, AGG, TACGGC, we basically get this solution over here. So we want to be able to end anywhere. So essentially our ending point is going to correspond to the cell in the table, in the matrix, with the largest value. So that's 4 over here. And when you do the trace back, you can see that this 4 is obtained from here. So you do a +2 to get this. So it's not obtained from here. So that's not going to work because that will be -2. So 2 minus 2 is not 4. But 2 plus 2 is 4. And there's another match here. So 0 plus 2. So that's going to correspond to G being aligned with G. And also the first G being aligned with this G. So that's our score. And we end here. So this is 0. That's where we stop. So whenever you reach 0, you stop. So that's the local alignment. So how do you actually do this? How do you fill out this table? So you can see how to fill out this table if you look at, so let me just put them side by side. So if you look at the recurrence, your first cell is going to be 0, right? And you can fill out the first row using the third case. So what you will do is the first row, you will look to your left, and you basically have 2 cases to consider. So if the gap penalty, if you have a penalty that is smaller than 0, then you will always get a negative value on the second case. So you're going to keep the 0. So the first row will be all zeros typically. The same thing for the first column. So with the first column, you actually have to look at the third case because J is greater than 0. And I equals 0, so you cannot use this case over here. So that's going to lead to that. And then when you look at an entry, so let's look at this 0 over here. So this 0 over here, there are 4 options basically. So the first option is to try to align A with T, so there will be a mismatch. So that's going to correspond to a score of -2. So A with T. So if I look at A with T, that's -2. So -2 is already smaller than 0, so we won't take that case. If you look at coming from the left, so that will be J minus 1. So that would correspond to a deletion. So that's going to lead to a cost of -4, which is smaller than 0. And the same thing is if you come from above, you will also have a cost of -4. So here we'll keep a 0. So that's basically what happens. Now if you look at this one, again, there are 3 edges, 3 incoming edges. So if we come from above, we will have a gap, so cost -4. From the left, also a gap, cost -4. But if we come diagonally, we will match A with A. So that would be corresponding to a score of 2. So that's the value that we pick, because 2 is greater than 0. So in any case, what happens here is if you look at your local alignment table, the scores in the table, there will be at least 0 everywhere. So that's really what happens. And you can reconstruct the alignment by looking at the maximum score in your table. And from there, you just do your backtrace. So that's what we did over here. Oh, and actually what's really cool about this program is, so when I stand on a cell, it shows me the scores of the 3 different cases corresponding to the edges. So if you come from the left, you have -4, because it will be 0 minus 4. No, actually, let's try and look at this. So what's the -4? Yeah, that's the gap. So the gap is -4. So if you come from the left, you would take the value from your left, 0, and you would do -4. If you come from above, you would also take the value above you and do -4. So that's local alignment. So what I encourage you to do is I encourage you to play with this tool, and actually not only play with this tool, but also try to do it by hand on a piece of paper, because in the midterm and possibly also in the final, there will be an assignment where you actually have to compute the alignment table using, for instance, local alignment. So you need to have done this at least a couple of times by yourself on a piece of paper. So don't only use this tool. Good. Let's proceed. So that's local alignment. Now, there's only one version left, gap alignment, and that's actually the hardest version. So let me motivate this. So let's look at let's actually think about our gaps. So suppose we have two input sequences, AAC and W equals ACA GGC, and let's say that the match score equals 1. So if the two sequences are identical, you get a score. If the two strings, if the two letters are identical, you get a score of 1, and mismatch is going to correspond to -1, and insertions and deletions will correspond to -2. So here I'm showing you two different alignments. So in both alignments, we have 3 matches and two, what are these? Insertions and deletions. Let's see. So we're inserting something in W and 2 insertions. So the score for both alignments will be identical. So it will be 3 times 1, score of a match, plus 2 times -2, the score of an insertion. So it will be -1 in both cases. But if you look at them, they actually look very different. So you could argue that maybe this one is better because the gaps are consecutive. And this is actually what's going on biologically. So if you have consecutive gaps, they are more likely. And the reason why they are more likely is because this could correspond to errors of your sequencing machine. So some machines actually tend to insert insertions and deletions like that of a certain size. But also biologically, there could be errors when a cell replicates its DNA, and these errors are known as slippage errors, and they correspond to 2 to 3 nucleotides. And in addition, if you think about DNA and protein, if you remember translating DNA, so first transcribing DNA to RNA, and then from RNA to protein. When you go from RNA to protein, you look at codons, you look at RNA nucleotides in triplets. So what you will typically have is if you delete a codon, you essentially delete an amino acid residue in your protein. So multiples of 3 are also very likely to observe. So we don't want to be splitting gaps. So we need to have a scoring function that's going to score this first alignment, or assign a larger score to this first alignment than the second alignment, where we split the gap, the stretch of gaps. So one such scoring function is known as affine gap penalties. So the idea is the following. So we have 2 scores, we have 2 penalties. So there is a gap open penalty rho, and there's a gap extension penalty sigma. So when you open a stretch of gaps, you pay the gap open penalty of rho. And then for every consecutive gap in this stretch, you will pay a penalty of sigma. So if you have a stretch of k consecutive gaps, the score of that stretch is going to be -1 times rho, gap open, plus sigma times k, extending k times with cost sigma. So if you look at these 2 alignments over here, the left alignment has only 1 stretch, and the right alignment, the rightmost alignment, has two stretches. So when we look at this one, here we pay the gap open extension penalty only once. So we have, so if we use a gap open penalty of 10, we will have, so the penalty incurred by this stretch of two gaps will be 10 plus 2, 12. So, and we have 3 matches, so essentially the score will be 3 minus 12, minus 9. However, if you look at this alignment over here, we have 2 stretches of gaps, both of 1 gap each. So the contribution of every gap, every stretch, will be 10 plus 1, 11. And it's a penalty, so we'll multiply by minus 1, minus 11. So we're looking at 3 minus 11, minus 11 again. So it will be 3 minus 22. So that's minus 19. So this is beautiful. This is exactly what we wanted. So the score of this first alignment is much larger than the score of the second alignment. So affine gap penalties result in low penalties for consecutive gaps than interspersed gaps. So that's exactly what we want to do here. So how do we compute this? So you could actually think about this. You could think about the edit graph to try to answer this question. So what we had initially in the edit graph, we had only the blue edges. So when you look at a vertex in the edit graph, the diagonal edge corresponds to a match-mismatch. The horizontal edge corresponds to a deletion, and the vertical edge corresponds to an insertion. Now, when you do affine gap penalties, you're essentially, rather than looking at gaps one at a time, you want to look at a stretch of gaps. So you're going to include all possible edges all the way to the left and all the way above you. And that's going to correspond to a stretch of gaps. And the penalty, the score that you assign to every edge, is essentially the affine gap penalty. So here we have just a single gap when we go from left to right. So that will be minus rho plus sigma. So here we have a stretch of 2 gaps. So that will be minus rho plus 2, so minus times rho plus 2 sigma. So that's basically what we have here. So we can extend the edit graph with additional edges and assign weights to those edges corresponding to the affine gap penalty. So what we're essentially doing here is we're basically extending the recurrence of global alignment. So we're inserting, so if I look at a vertex ij, I'm gonna insert, I'm gonna have a diagonal edge corresponding to I minus 1, j minus 1. And in addition to that, there will be I edges corresponding to deletions, and there will also be j edges coming from above you corresponding to insertions. So every vertex will have how many edges? Let's do the math. So we will have I plus j plus 1 edges. So the running time is simply going to be the number of edges, because each edge corresponds to a lookup in the table. So this can be done in constant time. So what we have is this left hand side over here. So that's the running time of vertex ij. Now, if you look at this I over here, so essentially we're summing I n plus 1 times. So what we can write here is you can just take out this I and replace it by I times n plus 1. So that's how we simplify this left hand side. So we get one summation here, and when you look at this j over here, the j is just summed n times. n plus 1 times. So we have I times n plus 1. And then we have plus this term over here. Now, we've seen this already. So when you take the sum of j from j equals 0 to n, that's the same as taking the sum of j from j equals 1 to n. J is 0 is 0. 0 plus something is that something. So this is going to correspond to this identity that we've seen before. So that's going to correspond to n times n plus 1 divided by 2. So let's use that. So we can replace this summation over here by n times n plus 1 divided by 2. And we do that n plus 1 times, right? So that's going to correspond to n plus 1 times this divided by 2. And now let's look at what remains. So what remains is n plus 1 times I. So we have n plus 1. We can distribute it out. So we get this over here. And again, we have the sum of I equals 0 to m. So by the same reasoning, that's going to correspond to m times m plus 1 divided by 2. And we do that m plus 1 times. So we'll end up with this running time over here. So this basically, this is the running time that we would have when we would do a naive affine gap penalty alignment. So we would have something that's m times n squared plus n times m squared. So if m equals n, what we will get is a cubic algorithm, n cubed. And we can do better than n cubed. So let's see how that works. So the idea is, if you look at affine gap penalties, there's actually 3 separate notions going on. So you open a gap, and then once the gap is opened, you extend, and then the stretch of gaps is over, and then you have a match or a mismatch. So we can capture these 3 separate notions using 3 recurrences. So the first recurrence, I'm going to indicate that using S right. That's going to be a gap in the first sequence. So that's going to correspond to an insertion. And we also have a gap in the second sequence. And we have matches and mismatches. So there's going to be 3 recurrences. And the idea is as follows. So the S diagonal recurrence, that's going to be the recurrence that corresponds to matches and mismatches. So our starting point is going to be the same. So this is global alignment again. So if I equals 0 and j equals 0, the score of S diagonal is going to be 0. And the score that we care about in the end is S diagonal at m, n. And what you can do is, at any point j is greater than 0, you can start a stretch of gaps in the first sequence. And similarly, if I is greater than 0, you can start a stretch of gaps in the second sequence. So let's look at those 2 recurrences that we have over here. So when we're inserting gaps in the first sequence, there's 2 things that we can do. So we can basically choose to extend an already open gap. So we will pay a cost of sigma, so that will be minus sigma. Or we can go back to our diagonal recurrence, to the match mismatch. So in that case, we insert 1 more gap and we have to close it. And we close it by paying the gap open cost. We pay rho. So that's what happens here in the S right. And in the S down, we do the same thing. So there's 2 options. You extend the gap without closing it. So you would just pay minus sigma, and you stay in S down, or you extend and close. In that case, you would actually pay the gap open penalty in addition to the extension penalty. So that's what happens here. And what you can do is at any point in the diagonal matrix, you can go to the S right matrix or the S down matrix with cost without actually incurring a cost. So you would still keep the same cost that you had in a matrix. So those are these two cases in the diagonal recurrence. So to compute this, you only need m times n time. So we have three matrices, and if you look at a cell in the diagonal matrix, there are essentially three edges. So you have a diagonal edge in the same matrix, or you have an edge to the same cell in the right matrix, or an edge to the same cell in the diagonal in the downward matrix. So those are the three cases. So let's try and see what actually happens here. So I just want to perform an alignment on an example. Okay, let's start with the base case. So in the base case, we have I equals 0 and j equals 0. So that's going to correspond to the diagonal matrix 0, 0, having value 0. So that's our base case. So now when we try to compute S diagonal 1, 0, I equals 1, j equals 0, there's only one case in the recurrence that we can use. So that will be this case. So we need to look at a downward matrix. So we're looking at a downward matrix over here. And to compute this value, so we have I equals 1, j equals 0, I equals 1. So there's only one case left. So this first case does not apply. So I equals 1 means that we have to look at the second case. And in the second case, what we do is we take our entry above us in the diagonal matrix, and we pay the gap open and the gap extension penalties. So that would be 0 minus 11. So that's minus 11. Excellent. Now, let's fill out this entry over here. So as I said, there's only one case that we can use. That's the downward entry. So that's going to be minus 11. Okay, now let's compute this one. So here I'm looking at I equals 2. So I equals 2 means that this case is enabled now. So there's two. So this case corresponds to extending the already open gap. So that will be minus 11, minus 1, minus 12. And the second case corresponds to essentially closing the gap. So we would go back to the diagonal matrix and pay the extension and the open. So that will be minus 11, minus 11. So that will be minus 22. So minus 12 is less than minus 22. So that's what we'll pick here. Good. Now let's look at this entry. So again, so this is I equals 2, j equals 0. So only this case is available to us. So this has to be minus 12. Excellent. Now let's look at this case again. So what do we have here? So we can pay gap open and close, gap open and extend, I mean. So that will be minus 12, minus 11, minus 23, or we can just extend. So that will be minus 13. That's what we're going to do, because that's less. So in this case, we will have, again, minus 13, because there's only one case enabled. Okay, good. So let's try and fill out this entry over here. So what are we looking at? We're looking at I equals 0 and j equals 1. So which cases are enabled here? So I equals 0 and j equals 1. There's only one case enabled. That's this second case over here. So we have to look at our rightward matrix. So in the rightward matrix, so we're looking at I equals 0, j equals 1. So only the second case is enabled. So the second case is going to correspond to taking the value of this cell in the diagonal matrix and doing minus 11, open and extend. So that will be minus 11 over here. So that's actually the value that we're going to pay here, because that's the only case that's enabled to us, -11. Now we can keep on doing this in the same way. So I'm not going to reason through this, but you can just do it yourself. So if I look at this cell, I need to compute this cell, and I can do -11, so that would be -22, or I can just extend. So we're going to extend. So this is what we'll get. All right, now let's look at the very first interesting cell. So we're looking at I equals 1, j equals 1. So there's a couple of options here. So if I take so I can take this rightward value. So we actually need to compute this rightward value over here. So what do we have? So I'm looking at I equals 1 and j equals 1. So j equals 1 means that only this case is applicable to us. So that will be -11 minus extend and open. So that will be -12. Wait, that's not -12. So that will be -11 minus 11. So it will be -22. And we also need to look at this value over here. So in this value we have I equals 1, j equals 1. So I equals 1 means that we cannot look at this case, we only look at this case. So that will be looking at this cell over here. No, actually, so we look at I minus 1, so we look at this cell over here, -11. And we pay the open and extension penalty, so that will be -11 minus 11. It's -22. Okay, now what we can do here is this case corresponds to a match, A with A. So there will be a score of 1, and we would come from here, so that will be +1. Or we could take this or this. So we will take 1. That's what's going to happen here. So that's the value we pick here. So I'm just going to, instead of filling this out by hand, I want to show you what this is going to correspond to when you do when you complete the table fully. So let's just go to that. So that will correspond to this table over here. So what I'm indicating here with the colors is the back pointer. So this allows you to do the trace back. So this is the score that we have in the end, -9. So when we do the back trace, so let's actually quickly do that. So I'm gonna do some borders here, corresponding to thick borders that will indicate the back trace. So we have -9. So we have a C and a C. So that corresponds, that could be a match. And actually, we have a match, because if you look at the corresponding entries in the down and right matrix, they are different from -1. So we must have come from here. And indeed, if you look at this, you have -10 plus the match score, which is 1. So this is basically the cell that we come from. Now let's look at this one. So again, we could not have come from the down matrix because it's not -10, and we could have also not have come from the right matrix because it's not -10. So what we instead have is a match. So that will be a score of +1, and indeed -11 plus 1 gives you -10. So that's basically our cell. And now we have a couple of options. So we could either go for a mismatch. Now actually, this is let's look at this. Oh, this is a match again. So we could go for a match and come from here. Or alternatively, we could also have come from here, which is also -11. So let's start with this one. So if we would have come from here, we basically get this cell. So we would have -12. -12 would correspond to this over here, and this -12 comes from -11, so that's an extension. and this extension comes from opening the stretch and also extending again from 0, 0. So our alignment in this case, let's just quickly write it down. So we would have C with C, we would have A with A, we would have A again with A, and then we would have, let's look at this. So we have C with a gap, C with a gap, A with a gap. So that's our first alignment. The alternative alignment, let's also compute that one. So here from -11, we could have come from, let's use a different line color for this. We could have come from, let's see, here. So that would be -11, and then this -11, we could have come from, let's see, the extension penalty from here, -10, and then we get the -10 from, see, from here. So that will be extend and open, and this comes from a match from here. Now let's see what that corresponds to. So we would have the same thing at the start, C with C, that's this cell. We would have A with A, so that would correspond to this edge from -11 to 10. And then rather than doing this edge, we actually go to here. So that would correspond to this edge. So that's going to be, let's see, A with a gap. So we are here, we have the gap, and then what we do is we have another gap here, so that will be this with C, and finally we have this match, A with A. So that will be the second alignment. So those are our two solutions. Good. So then the naive algorithm that we've looked at for gap penalties supports arbitrary gap penalties, right? So what you could do is you could have a penalty function that takes as an argument the length of the gap. And essentially what you would do is, in this extended edit graph, you would label every edge by the value of this gap penalty function. So this is going to result in a running time of mn times n plus n. So we've seen this. So we also saw that with affine gap penalties, you can actually do better in this. You can maintain 3 tables and have a running time of n times n. It turns out that more complex functions, that there is something actually in between the naive algorithm, which would have this running time, and the linear time algorithm for affine gap penalties. So this plot nicely illustrates such functions. So what we saw was an affine gap penalty function. So here the gap open penalty is 2, and the gap extension penalty is, what is it? Let's see. 1 over 5. So you basically, a stretch of 5 caps has a penalty of 1. So an extension would be 1 over 5. But you could also look at more complex functions, like convex functions over here, like this purple function. So in the Gusfeld book, there's a really nice algorithm showing you that you can do this in mn times log m time. So I guess there's some binary search happening there. So to conclude, in today's lecture, we start with a small recap of global alignment, which is the longest path in a DAG. And we've seen that different kinds of alignment algorithms or alignment problems can be represented with small tweaks in the graph, where the number of edges that we add is very small. It's actually constant, leading to the same running time. So today's topics are also described in the book 6.7 to 6.9, and please take a look at the lecture notes. Homework assignment 1 is due next week, Monday, by midnight. If you have any questions, please contact me or TA. Thank you.